Welcome back, everyone. This is going to be our Unit 2 of AP Physics C Mechanics. This is going to be the Dynamics unit. We're going to be discussing forces. And integral to our understanding of forces is going to be our understanding of the center of mass of an object. We're going to start our discussion off with center of mass. And you'll notice that on your equation sheet, there are two equations given to you for center of mass, which I will explain in just a moment. And I will explain also why they are the same equation. Just one in discrete form, one in continuous form. What is discrete and continuous? Because we're going to need to understand that difference for our entire understanding of physics. Number of people is a discrete number, okay? I can only go up by one. I can have one people or I can have two people. I can't have 1.24 people. Like, for example, weight can be a continuous quantity of weight. You can weigh 1.6423896 kilograms. All right, that is an example of a continuous metric. This equation stands when you are dealing with a system with a continuous number of particles. This is for a discrete quantity where you have a finite number of participants. An example of the discrete system, of the finite system, is if I have three balls and they're not attached to each other, they're just three distinct objects, and I want to find the center of mass of this system, okay? The system just being defined as the place where the balls reside. If we tried just by looking at it, and let's say I told you that all the balls are the same weight, you'd say that the center of mass is right around here. You consider them as a point mass, okay? That is in contrast to the continuous example, where, for example, you might be given a rod or a beam, a single object, and you would be asked to determine the center of mass of this beam in the vacuum, where the bounds of our system are the beam. You would be given some function to represent the density of the beam, like let's say the beam is a lot more dense on the right than it is on the left. Then this equation would help you determine the exact location of the center of mass within the beam, okay? So where does discrete and continuous come into play? Well, here you have a discrete number of objects, a finite number of objects that are contributing to the location of the center of mass. In this example, you are considering the contributions of every infinitely small slice of the beam, okay? Because you're trying to determine the center of mass within the beam, okay? So it would be analogous to considering the contributions from every atom within the beam. There's a continuous, approximately infinite set of contributions that you are calculating as to where this center of mass is supposed to be. Let's consult an example with this equation right here. So what are the equations actually telling us, okay? This side of our equation, the x coordinate of our center of mass, that's what it means. Now, r and x and d are often used interchangeably because all three of them mean distance or displacement. Okay, so you can very often use x or d or r to represent the same quantity. Okay, to make my life easier, I'm going to continue using x. What is the top half of our equation telling us? It says that we're going to multiply the mass of a contributor times its x distance. And so the more massive it is, or the further it is from our reference point, if we're calling this our reference point 0, the further it is from 0, the greater contribution it will make to the location of our center of mass, okay? So to better facilitate that understanding, let's call this edge right here let's call this right here our 0 reference point, okay? So the x distance from this point to our reference point is 0. The x distance from this point to our reference point is 0. X is 0, and 0 multiplied by anything else is 0. So that leaves with the contribution from this particle. What is the displacement in the x direction for this particle? Let's say it's 1 meter. So the mass of this particle is m, let's say 10 kilograms, 10 kg times 1 meter divided by the sum of all the masses. So even though these two objects are at a 0x displacement away from our reference point, they still have mass, so they're still going to participate in our denominator. So if all three balls have mass m, that means the sum of all our masses is 30 kilograms. Okay, so 10 divided by 30 is 1/3. Therefore, the x position of our center of mass is positive 1/3. Okay, so with reference to our 0 point here, our center of mass would be 1/3 of a meter, which is right about there. Because I said that this ball was a 1 meter distance away from our reference point. So our 1/3 would be right about there. Okay? This equation is the same exact thing. It's just analyzing when we have an infinite amount of particles to consider. Okay? So on top here we have the same x, the same x distance away from our reference point, multiplied by what? Multiplied by the mass differential. Okay, we had x multiplied by mass here, and we have x multiplied by mass here. If you remember what a mass differential is, it is a infinitely small mass. So we're taking an infinite sum of infinitely small masses divided by the total mass, which means the infinite sum of all the mass differentials. Okay, so the denominator is your total mass in both cases. So now let's observe this equation, because this is going to be the equation we're largely going to be working with. So given that equation, you would be given problems that give you functions, because when we're dealing with integrals, when we're dealing with calculus, that means we're dealing with functions. What kind of function would you be given? You would be given a function for density. Okay? A linear density, or any type of density, will usually be expressed as lambda as a function of x, or as a function of r, because again, these are interchangeable, or rho as a function of x or r. Let's say that you're given a problem that states the linear density of this rod, if we define our 0 point at the left side and our right side is defined as the length of the rod, L, the linear density of the rod, lambda of x, equals, let's say, 4x squared. So just looking at that equation, we know that on the left side of the rod, we're going to be much less dense, and on the right side of the rod, we're going to be much more dense. What do we do now? This is why it's so important to understand units, okay? Because units are often the key to solving your problems. What is density? What is density? It's mass over volume. In this case, we're dealing with a linear density. So a linear density is mass divided by length. That is our clue, okay? If I have a lambda, I am in units of mass over length. And since this is a continuous function, it's not just mass over length, it's the derivative of mass with respect to length. Because if I were just given a constant number like 4, that would be my total mass divided by my total length. But I have a function, and since a function is continuous, it will be a derivative if it involves division. So linear density is always your dm dl. In this case, length is represented on the x-axis, so we can call this dm dx. If instead we were given a function of r, this would be dm dr. But that is the important distinction to make, that whenever you're given density, it's going to be dm dr. If you're given area density, it's going to be dm dA. If you're given volumetric density, it's going to be dm dV. Why is that important? We need to know dm. Okay? How do we find the mass differential? How do we calculate our dm? Well, we have dm here. So, if lambda of x equals dm dx, then I want to get dm by itself. So, dm equals lambda of x dx. Okay? So now I have my mass differential. Now I know what my mass differential is, so I can plug it into these equations. So the x-coordinate of my center of mass is equal to the integral of x times dm. So x times dm is lambda of x, which is 4x squared, times dx. Okay, divided by the integral of dm, which is just the integral of 4x squared dx. So that is how we derive and solve our equation for center of mass. Now this, you would just plug into your calculator, you would carry out this multiplication and say that this is now 4x to the third dx over the integral of 4x squared dx. Okay, you would pull both the 4's outside of your integral signs, and they would cancel as a result of that. If we bring this up here, we are given that the x location of our center of mass is equal to the integral of x to the third dx over the integral of x squared dx, okay? Now is the time we take a step back and we ask ourselves, are these supposed to be indefinite integrals or are these supposed to be definite integrals? And how do we know? Well, we look at the left side of our equation here, the x-coordinate of the center of mass. Okay, the rule is, if we are trying to find a function, these are indefinite integrals. If we are trying to find a number, these need to be definite integrals. And that goes for everything in physics. The coordinate of our center of mass, that is one finite number. So therefore, these need to be definite integrals. So how do I find my bounds of integration? I am integrating from my 0 to my final distance. I am integrating over the whole rod. I am summing up all of the infinitely small masses from the one tip of the rod to the other. So my bounds of integration are going to be one end of the rod to the other end of the rod. And if I want to give one end of the rod to the other end of the rod in terms of x, my lower bound would be 0 and my upper bound would be L. Okay? Now let's just say that our L is 4 meters, then it would be 0 to 4. And we would evaluate both these definite integrals, and that would give us the location of our center of mass in the x-axis, okay? If you, again, had a different density equation that gave you a density as a function of y, you would do a second equation. You would do a second plugging in of this formula, and that would give you the y-coordinate of your center of mass. And then if you're dealing in 2 dimensions, you would combine the x and the y-coordinate to give you your ordered pair in 2 dimensions. Okay. So I know it is a very daunting topic, and if you guys ever need extra help on something like this, come to your calculus teacher, your calculus professional. I have a Discord server specifically designed so that you guys can come and ask me questions or ask other kids questions. That's out there if you need, okay? Link in the description. So let's move on, okay? From there, what is the importance of the center of mass? Why are we calculating it? Well, the importance is actually very significant because when you calculate the center of mass, you are able to treat the system as if the entirety of the mass were concentrated at the center of mass. You're able to treat the system as if you are dealing with one tiny speck and then all of your mass is concentrated at that one speck, at the center of mass. I know it's a little difficult to conceptualize, but it works. If any force is acting on an object, you can interpret that force as acting on the center of mass. And the center of mass is going to be a word that we use as we go on with the rest of the unit defining forces and defining Newton's laws, okay? So let's get into that first of all, okay? The first thing we're going to deal with forces is the free body diagram. What's a free body diagram? It's you have an object represented by a dot, and you are asked to draw all of the forces acting on that object. Like for example, me. Let's say Meek is that dot, okay? What are the forces acting on Meek right now? Well, there is the gravitational force pulling me down to Earth, and there is something called the normal force, that the floor is pushing back up on me. That is going to come into Newton's third law that we're going to discuss in just a moment. So if we wanted to draw the free body diagram for Meek, the force of gravity would be pulling him down, while the normal force, the force of the floor pushing me back up, would be pointing up. So that the force of gravity and the normal force from the floor are completely balanced. Okay? What does it mean when forces are balanced? It means that Meek does not have an acceleration. He's not moving. His velocity isn't changing, okay? If now my friend were to come and shove me from my left, then the force of my friend that he applies to me would be represented on the free body diagram. He would push me to the right. So he would apply a force to me towards the right. So the important things we need to consider about free body diagrams is that each force should be labeled. Each force needs to be represented as an arrow, starting on the dot and pointing away from the dot. Each force needs to be drawn in the correct direction of which it is being applied. And each force must be drawn with respect to scale. What does that mean? It means if the force of gravity and the normal force are equal to one another, their arrows must be the same length. Newton's first law. An object at rest stays at rest, and an object in motion stays in motion until acted on by an outside force. That means that if Meek is standing still right now, Meek isn't going to start moving until he is acted on by an outside force, okay? What would be an outside force in this equation? Meek moving, or Meek's friend shoving him, okay? Usually, when we are considering physics problems, we don't consider the fact that the objects we're considering have the power to move themselves, okay? We don't usually consider humans in physics, okay? So that when we speak of external forces, we literally mean a force from the outside coming and pushing you and acting on you in some way. The second part, or an object in motion stays in motion until acted on by an outside force, okay? That means that you could be moving with some velocity. Let's say you're moving with a velocity of 10 meters per second to the right. That would mean that you will continue moving at 10 meters per second to the right indefinitely until an outside force acts on you. Why doesn't that happen on Earth? It's because wind resistance is an outside force, because friction is an outside force, because the wind itself is an outside force. Also because of the second law of thermodynamics, but you should go take AP Physics too if you want to learn about that. Anyway, what's the second law? The second law is what we are largely going to concern ourselves with for the majority of all math in this class. F equals ma, or as it's given to you on your reference table, A net equals F net over m tot. Okay? Force, capital F, equals mass times acceleration. What does that mean? Well, first we understand what acceleration is from calculus. Acceleration is the rate of change of our velocity. If the acceleration is zero, means our velocity is not changing. That's why the second clause in Newton's first law is true. If you have no external force acting on you, your force is zero, that means your acceleration must be zero. So your velocity must remain constant. So a constant velocity means you're either moving or you can have the constant velocity of zero in which you're standing still. So if I apply a force of 100 newtons to a tennis ball as I throw it, the mass of the tennis ball is 2 kilograms, then 100 newtons divided by 2 kilograms equals an acceleration of 50 meters per second squared. Net force is important to consider, okay? Net force is analyzed when we draw a free body diagram, okay? If I were to revert back to the fact of the previous example where I had the force of gravity pulling me down and normal force from the floor opposing the force of gravity, I would say that the force of gravity is equal in magnitude to the normal force, but they're in opposite directions, okay? And this is where vector addition comes into play. Vectors are added tip to tail. So if I draw the normal force vector and I draw the gravitational force vector tip to tail, and I leave and I get back exactly where I started, that means the two vectors exactly cancel each other out. So the normal force vector plus the gravitational force vector in this case is zero, because they are acting in opposite directions with equal magnitude. Therefore, when I sum up all the forces, I believe it's given on your reference table like this, sum of all the forces. If the sum of all my forces is zero, then my net force is 0. So 0 divided by anything results in 0 acceleration. That's why if I stand still, I'm not accelerating. But once you introduce the force of someone pushing Meek, that force is not being opposed by anything, okay? That force is allowed to impart an acceleration onto Meek, which is why he falls to the right when you push him, okay? Alternatively, you could have a small force of friction that opposes Meek's movement to the right, okay? In that case, Meek would still have an acceleration to the right, it would just be less now because the force of friction is acting against the force being applied to Meek. Finally, Newton's third law, which is important in and of itself, is that an object, when acted on by an outside force, will impart an equal and opposite force onto the object acting on it. So for example, if I take my hand here and I apply a force to the whiteboard pushes back on me, okay? That is that the applied force of my hands to the whiteboard is equal to the normal force with which the whiteboard pushes back on me, okay? So my net force in this case is 0. How do I know that? Because the whiteboard is not accelerating. Whiteboard has not changed position. Whiteboard was at rest and it has stayed at rest. By Newton's third law, each force generates an equal and opposite force. If you weigh 60 kilograms on Earth, the Earth weighs 60 kilograms on you, okay? Everything in the universe has mass, therefore everything in the universe exerts a gravitational force on everything else. If the Earth attracts me, I attract the Earth. In that case, let's actually delve into the mathematical representation of the gravitational force. So we have two equations for this, and it's important to understand the difference, okay? Let's start with the fundamental equation first. The force of gravity for any object in the universe is equal to a constant, big G, as it will be referred to henceforth, times the mass of an object multiplied by the mass of the other object. So what do I mean by that? If we're considering the system of me and the Earth, m1 would be me, m2 would be the mass of the Earth. m1, m2 divided by the distance between those two masses squared. Okay, notice how r in this case is used to represent distance, not radius. So these letters are interchangeable, x, r, and d. Okay, but the first thing you might be thinking right now is, wait a minute, I'm standing on Earth. There's 0 distance between me and Earth. No, you're wrong. There is 0 distance between you and the Earth's crust, but remember that whenever we're considering anything, we need to consider that mass is concentrated at the center of mass. Where is the center of mass of the Earth? It's right in the middle, right at the core, okay? So this distance, this radius, is not the distance between the two objects, it is the distance between their centers of mass, okay? And for any distance ever you will analyze in your physics class, you are not considering the distance between the edges of two objects, you're considering the distance between their centers of mass. From this equation, we can derive the more conventional equation we use, which is the force of gravity at Earth's surface, okay? So the force of gravity at Earth's surface is what? It's going to be our g multiplied by the mass of the Earth multiplied by the mass of the object divided by the radius of Earth squared. So first things first, when we're deriving our equation, is let's try and separate between variables and constants. G is a constant given to you on your reference table. The radius of Earth isn't changing, so that's going to be a constant. The mass of Earth isn't changing, so that's going to be a constant. What's the only thing that's going to be changing here? The mass of the object that you are analyzing with. So we can say that the force of gravity at the surface of Earth is equal to this big constant times the mass of whatever object you're using, okay? And if we do the math and we calculate the gravitational constant g multiplied by the mass of the Earth divided by the radius of the Earth squared, we get that the force of gravity near Earth's surface equals a new constant g times m. Okay? And what does this look like? This looks like Newton's second law. Force equals mass times acceleration, where little g in this case is the gravitational acceleration constant. Okay? And we can analyze it at the second level here. If Fg equals g m1 m2 over r squared, and F equals ma, then we can say ma equals g m1 m2 over r squared. We can eliminate a mass from both sides, and we can say that the acceleration from the force of gravity on any given planet at any given radius is equal to g m2 over r squared, where m2 would be the mass of the planet. Now you might be saying to yourself, but wait a minute, if I jump up or if I raise myself above the surface of the Earth, then the radius of Earth, the distance from me to the center of the Earth, changes. Yes, it does change, but the change is negligible. What do you mean the change is negligible? I mean, the radius of Earth is 4,000 miles, okay? If I, let's say, go up in a high-rise skyscraper in New York City, well, what's the height of that? Maybe half a mile? It's the difference between 4,000 miles and 4,000.5 miles, okay? It's not a significant change. Therefore, we can assume within maybe 4 miles, if we assume negligibility to the 1,000th degree, then within 4 miles of Earth's crust, this is the equation you're dealing with, okay? And that is the equation given to you on your reference table. The force of gravity equals the mass of an object times the gravitational acceleration, g. It's important here to note the difference between mass and weight. Very simple thing to understand, okay? Everything has mass. Mass is determined by the amount of subatomic particles that make up something, okay? Sounds complicated, it's not. How many particles make up Meek? There are more particles inside Meek than there are in this marker. Therefore, Meek has more mass than the marker, okay? But there are some cases where we consider density, where two objects with the same mass, sorry, not the same mass, the same volume, two objects that take up the same amount of space, one has more mass than the other, because one can store more particles in it than the other, okay? So your mass can never change. You can never lose particles, okay? I'm not just going to suddenly lose an arm and my mass is going to decrease. That's not what happens, okay? You assume mass stays constant unless you physically slash the mass in half and break apart whatever object you're dealing with, okay? So your mass never changes, but your weight can change. Why can your weight change? Because your weight is the force of gravity, okay? So if you change the planet you're on, if you change the mass of the planet you're on, or if you change the distance you are from a planet, then your weight's going to change, okay? Because the force of gravity changes. There you go. So let's discuss the importance of the center of mass assumption, okay? If I'm dealing with the Earth and the Earth's moon, okay? If I were calculating the force of gravity of the Earth on the moon, I would need to calculate the force of gravity from this chunk of Earth on that chunk of the moon, and of this chunk of Earth on that chunk of the moon, and of this chunk of Earth on this chunk of the moon, and of this chunk of Earth on that chunk, and you get the idea. You'd need to do an infinite number of calculations because the distance between this side of the Earth and the moon is different from the distance between this side of the Earth and the moon. So how do we solve that? Well, we can say that the entirety of the moon's mass is concentrated at its center of mass, and the entirety of the Earth's mass is concentrated at its center of mass. So the radius, or the distance we're considering, is merely the distance between their centers of mass, okay? There is one situation where the center of mass assumption does not hold. What is that situation? When you are trying to calculate the gravitational force between two items where one item is inside the other. Like if I'm trying to calculate the gravitational force exerted on a person in Earth's mantle. Like, that's where things become more complex, okay? Because at this point, the Earth's mass is sort of divided in two like this. This side of the line is pulling you closer to the center of the Earth, while this side of the line is pulling you further away from the center of the Earth. So, where in this example, all of the mass was pulling the two objects together. Where in this case, some of the mass was contributing to a gravitational force in one direction, while the rest of the mass is contributing to a gravitational force in the other direction. Okay? So here is where we need to consider what fraction of the mass is contributing to a net inward pull. Okay? Because a gravitational force is always an attractive force. So the way we analyze a problem like this is, let's say I have an object right here. I would need to calculate the amount of mass that is still pulling me towards the center of the Earth, okay? So I would draw a perfect circle, or if this is a three-dimensional Earth, a perfect sphere, around the center of the Earth such that the edge of the sphere is right where my object is, okay? So this circle basically represents all of the mass that is still on the left side of the object, all of the mass that is still attracting the object towards the center of the Earth, okay? Such that all of the mass here is pulling the object to the center. All of the mass on this side is pulling the mass away from the center. And if we draw our separation line right here, all of this mass is pulling the object away. All of this mass exactly cancels out the mass that's pulling it away, okay? But there's so much more mass on this side. Wouldn't there be a net force towards the left? No, because your gravitational force is dependent on the distance from the mass, okay? So this small amount of mass pulling you to the right applies a much greater force than the same amount of mass on the other side pulling you to the left, okay? So if we draw this circle, all of the mass on this side of the line exerts a gravitational force that exactly balances all of the mass on this side of the line, okay? So the only net force that we need to concern ourselves with is the mass applying a gravitational force within this sphere. In order to calculate this mass in this sphere, we would need to know the density of Earth, okay? And as we know, the density of Earth is not constant. The center of Earth is exponentially more dense than the Earth's crust, okay? So the density of Earth would be a function of radius, or a function of x, a function that increases as you get further away from the center, okay? Let's say that it increases logarithmically. So your density as a function of r would be 4 times the natural log of r, okay? And what did we discuss that density is? In this case, since density is a function of r, our density is dm dr. Again, I am trying to find the total amount of mass in this sphere, the sphere that is just barely touching my object. Virtual sphere, of course. So I need to find the sum of all the mass. So I need to isolate dm. So dm equals my density function dr. This was for a mass differential at a certain point, okay? This equation gives us a differential mass for a certain point along a rod, okay? But here, we are trying to analyze a contribution from many different points, okay? Because if you look at a sphere, there are many different points that are at a given radius from a sphere, okay? If you look at a tennis ball, let's say the radius of that tennis ball is 4 centimeters, then there is a lot of green fluff that is 4 centimeters away from the center. 4 centimeters away from the center does not specify a single point. It specifies all the points on the outside of the ball, okay? So this equation is only giving me the mass of a single point, but I want the mass of all the points on the edge of the ball. So how am I going to do that? Well, I need to calculate, how do I calculate all the points on the edge of a ball? That's the surface area of a sphere. Surface area of a sphere is, I believe, 4 pi r squared. I am trying to get my single point on the surface area, and I need to multiply that by the whole surface area to get the total differential mass of the surface area, okay? Let me try and think of a better way to put this, okay? If I'm trying to, if I know how much green fluff is at a single point on the tennis ball, I know that if I multiply that single point, the amount of green fluff in that single point, by the total surface area on the ball, then I will get the total green fluff on the ball. That's effectively what we're doing here, okay? So my differential mass at a point times the surface area of the ball gives me the differential mass of the entire shell of the ball, okay? Because since density increases as we go further away from the center, the mass of each cell, the mass of each surface area is going to be different. So we're going to need to take an infinite sum of all of the infinitely small surface area shells to get the total mass of this sphere, okay? So we're going to take our dm times surface area, our rho of r times dr times 4 pi r squared. And you'll know you're doing this right because your differential and your variable line up. That whole expression right there gives us the differential mass of a single surface area within the sphere. Okay? So when we're going to take the infinite sum of the masses of all those surface areas to get the total mass of the sphere. Okay? Now that we have our dm, we're just going to take the integral to get the infinite sum. And what are we looking for? We're looking for mass. Okay, mass is a single finite number, which means we're looking at a definite integral. How do we know the bounds of integration? Well, we're integrating with respect to radius. So we'd be integrating from our center, which is 0 radius, all the way up to the final radius of our sphere, okay? How do we know the final radius of our sphere? If I gave you the total radius of Earth being 4,000 miles, and I gave you that the object had sunk into the Earth's crust by 500 miles, then the remaining radius would be, 500, would be 3,500 miles. So we'd be integrating from 0 to 3,500. And we have some constants here. So let's make sure we isolate those. 8 pi times the natural log of r times r squared dr. Hey, you're given a graphing calculator on this exam. Do not try and do integrals by hand. Just plug them into your calculator, okay? If you're unsure of how to do that, come here. It's not just putting it into y equals. That takes so much time. Okay, watch this. I'm going to have my calculator here. Let's see, can you guys see this? Yeah, let me bring it closer like this. I'm going to clear everything out. I'm going to go down here to the math button. See a bunch of options pop up here. Just press the number 9. And look what I got here. I'm going to go from 0 up to 3,500 miles. I'm going to go to the left of my integral. I'm going to press second delete, which is insert. And I'm going to press 8 second pi. And I'm going to place my function inside the integrand, which here is going to be the natural log right down there of x multiplied by x squared. Where's x? There it is. squared dx. And you would just get your result like that. Must be a pretty big number. Yeah. So let's try and remember for a minute what we're trying to calculate here. The total mass of this sphere, okay? That gave us our total mass, big M. But the problem asked us for the force of gravity acting on the object. So we would need to pull back out our force of gravity equation and say that the force of gravity on the object right now is going to be our big G times the mass, the partial mass of Earth that we calculated, times the mass of our object divided by, we already solved for the radius between the two, 3,500. And that's how you would calculate your force of gravity in this particular case. Let's move on to our discussion of types of forces. First of all, the frictional force. Okay? Two types of frictional forces. Static friction, kinetic friction. Okay? Static friction is friction that is applied when an object is not in motion. What do we mean by that? Static friction is, let's say, I place my hand on the wall. Okay? My hand is being acted on by the force of gravity right now, which means my hand is trying to fall towards the ground. Okay? Static friction is the friction of the wall that is opposing the force of gravity right now. It is the force of friction that is opposing movement. Okay? It is the force of friction that acts when the object is not moving. Okay? In contrast, you have kinetic friction, which is the frictional force that is acting on my hand as my hand is in motion, as my hand is falling towards the ground. Okay? Your reference table gives you the equation for calculating the frictional force, as the frictional force is less than or equal to the coefficient of friction times the normal force. Okay? How do we calculate normal force? Well, you look at your free body diagram. Okay? If I draw a free body diagram, and let's say I have a gravitational force acting on me, downward. Okay? Let's say we're trying to calculate the normal force of the floor that's pushing up on Meek right now, okay? We know that when we draw a free body diagram, there is a gravitational force pulling down on Meek, and there's a normal force pulling up on Meek, okay? The gravitational force and the normal force are equal in magnitude, opposite in the direction in this particular case. Why do I say in this particular case? Because I'm not moving. That's how we know they're balanced, okay? So we can say that the magnitude of the force of gravity is equal to the magnitude of the normal force because their directions are not equal. That means mg equals Fn. Therefore, in this equation, if I am calculating frictional force is less than or equal to mu times mg. Okay? Now, if let's say I have a child on my shoulders, like I'm walking him, then there is the force of gravity acting on Meek in addition to the force of gravity acting on the child. Okay? Which means, since in the up-down direction we are not moving, I'm not falling through the floor, and I'm not shooting straight up into the sky, I have zero acceleration, that means that Fg1 plus Fg2 has to equal the normal force, okay? Because the forces are balanced. So mg1 plus mg2, you get the idea. You're going to have to derive a method of representing your normal force depending on what situation you're in, and you're going to use your free body diagram to understand what your normal force is comprised of. Okay, so that leaves us with the coefficient of friction. Coefficient of friction is always going to be something that is either given to you or is something that you are being asked to determine. Okay? We're not yet at the level where we've unlocked a sufficient number of equations to determine coefficient of friction, so specifically for this unit you will always be given coefficient of friction. So what is this less than or equal to sign? Okay? When I'm dealing with static friction, and I'm dealing with a coefficient of static friction, depicted as such, static friction always opposes the force that is trying to move it, okay? So if I place my hand against the wall, and how would I calculate normal force in this case? The normal force, the magnitude of the normal force is equal to the force with which I am pushing on the wall. So if I push on the wall harder, the wall is going to exert a greater normal force on my hand, okay? The gravity is trying to pull my hand down, okay? But static friction is keeping it in place. If I myself try and push my hand down too, then the force of static friction increases to oppose now both the force of gravity and the force of me pushing down on my hand, okay? So that's what the less than or equal to sign means. The force of static friction can increase to oppose a greater amount of force up to a certain point, up to this point on the right side of the equation, okay? So the force of friction can be less than that if the force it is trying to oppose is less than that. That is in stark contrast to kinetic friction. The force of kinetic friction is always equal to the coefficient of kinetic friction times the normal force. The kinetic friction force is always a constant. That's why it has a hard equal sign. Okay, moving on from there, we have resistive forces. Most common example of a resistive force is air resistance, okay? A resistive force is a force that is defined by this equation. I don't believe this is on your reference table, okay? So what is this equation telling us? The resistive force is equal to some constant k times the velocity of the object. What does the negative mean? It means that the force vector always acts in the opposite direction as the velocity vector. So if I throw my pen across the room to the right, that means the resistive force from air in the room is going to apply a force to the left to oppose the movement of the pen, okay? So the greater the velocity with which my pen moves through the air, the greater the resistive force upon the pen by the air, okay? It's pretty simple to understand. What resistive force is often used is to assess your knowledge of differential equations. Let me demonstrate that in just a moment. We know that force is equal to ma by Newton's second law. The mass of an object times its acceleration is equal to a negative constant times the velocity of the object. We know that the acceleration of the object is dv by dt, and therefore we can rewrite this as m dv dt equals negative kv. And you could be asked to solve this differential equation for the velocity function. So if I were to do that right now, what do we need to do for separable differential equations? Well, we need to isolate all of our variables. So we have a dv and a v, and we have a dt, and we have an everything else. Okay, so I am first going to write m dv equals negative kv dt. I'm going to split up my differentials. Then I'm going to get 1 over v dv equals negative k over m dt. Okay? Negative k is a constant. Your mass doesn't change, so your mass is also a constant. And we're going to bring this up here, integrate both sides. 1 over v dv equals negative k over m times the integral of dt. Okay. We are solving these integrals to solve for a velocity function. Therefore, these are going to be indefinite integrals. We do not need to specify bounds of integration. Okay, moving on from there, we have a discussion of the forces in circular motion. Now we're going to cover circular motion much more in depth in a later unit, but for right now, we're covering centripetal force. Okay, centripetal force is probably a word you've heard of before. But let's understand what exactly is going on here. Since you guys are only studying calculus in one-dimensional space, this is going to feel a little new to you, okay? So let's say I have a race car, okay? And my race car is moving around a circular racetrack, all right? So the velocity of my car let's say is constant. So the change in my velocity of the car is 0. let's specify that the change in the magnitude of the velocity is 0. Because as we can clearly see, as the car drives around the track, the direction of its velocity is continually changing, okay? So let me ask you this. If the magnitude of our velocity is 0, but the direction of our velocity is changing, do we have an acceleration? Yes, we do. Because the acceleration does not need to act on the magnitude of the velocity, it can act only on the direction, right? So if I, let's say, shoot a bullet towards the right side of the room, you would need to apply a force to that bullet in order to drive it further forward or drive it further backward, okay? Even though you're not changing the velocity, the speed of the bullet, in order to change the direction, you need to apply a force to it. And applying a force implies the applying of an acceleration. Okay, so we do have a force acting on this race car. So on your reference table, you are given the equation that a centripetal acceleration is induced on the race car, and that centripetal acceleration is equal to the velocity of the car squared divided by the radius through which it is orbiting. Okay, you are also given that as equal to the radius times omega squared, but we are not going to be dealing with this as of right now. We're going to get to that in just a moment. Okay, first off, pay attention to just this. Okay, so we have a centripetal acceleration. How do we get from centripetal acceleration to centripetal force? F equals ma. So I need to multiply my centripetal acceleration by a mass in order to get the centripetal force acting on the race car. Okay? So if I have a race car going directly north and I'm trying to pull it in this direction, which way is my force going to be acting? That's right, it's going to be acting in this direction. Therefore, force is always acting perpendicular to the direction of motion, okay? Therefore, my centripetal force is always acting perpendicular to the edge of the circle and always pointed towards the center of the circle, okay? Think of when you're spinning a string around, okay? Centripetal force that is acting on the edge of the string is the force of tension in your string, okay? And where is that tension force directed to? The tension force is directed along the length of the string towards the center of rotation, which is your hand as you're spinning, like, let's say, a whistle around your hand. As the velocity of the car increases, a greater centripetal force is required to maintain the circular path. A greater centripetal force is required to prevent the car from spinning out of control. That's why whenever you're in a car and you need to make a turn, let's say a right-hand turn, you slow the car down, okay? In order to make a very controlled, very precise right-hand turn, you want to have as little centripetal force as possible. How do you minimize centripetal force? You minimize velocity, okay? Also, you could make a wider turn by increasing radius, all right? Aside from that, another type of force is the force applied by a spring, okay? We know that when we compress a spring, it will try and decompress and launch us backward. And as we stretch a spring, it's going to try and recompress and pull us back inward, okay? So the force of a spring is simple equation, negative K delta X, and that is for an ideal spring, okay? K would be the spring constant. Delta X would be the distance through which the spring is either compressed or stretched, okay? So if I draw a spring like here, and I compress the spring this distance, that's going to be my delta X. If I compress it that distance, the spring will try and force me back this way, okay? That's why the force vector is opposite the displacement vector, as indicated by the negative sign. K, like I said before, is a constant, and your delta X is can also be your distance by which you extend the spring. And in that case, the spring would try and recontract this way. Back to circular motion for a second. Circular motion can be analyzed using period and frequency because it is a reoccurring event. Okay? If you have an object moving in circular motion, then that object will pass through a certain point many times, and it'll follow the same path over and over again, okay? So here is where our omega comes back into place, this symbol, okay? Omega is the unit which denotes angular velocity. Angular velocity is d theta by dt, where linear velocity, v, was dx by dt, or dy by dt, depending on the axis with which you're analyzing. Since this is a circle, instead of traveling through a distance, I am traveling through an angle, okay? Since there are 360 degrees in a circle, a complete revolution would be traveling through 360 degrees of a circle. V equals R times omega. Very, very useful equation. And I'm kind of upset now, because there were so many kids in my class who got so many problems wrong because they forgot this. And now you guys get it on your reference table. It's crazy. Anyway, your linear velocity, meaning the linear velocity of this race car, is equal to the radius of the sphere multiplied by its angular velocity. Consequently, you can calculate angular velocity by just doing a little bit of algebra, okay? So you can see that centripetal acceleration can be calculated using either form of velocity. Period, what is period? Period, you have equations defining period on the right-hand side of your equation sheet at the very bottom. Period is the time that it takes to complete one revolution. Okay, so since period is time, it's going to be units of seconds. You will see that period is equal to 1 over frequency. What is frequency? Frequency is how many revolutions does it complete every second, okay? So if it takes 5 seconds to complete a revolution, it means it completes 0.2 revolutions every second. So the units of frequency are 1 over seconds, or hertz. You're also given that your period, t, is equal to 2 pi over omega. So if I wanted to calculate the period of the race car moving around the track, I would need to know the angular velocity omega, or I could calculate angular velocity by just doing velocity over radius. Alternatively, you can write that as 2 pi times radius over velocity, as with this substitution, okay? We're going to be delving much deeper into springs and circular motion and all this in subsequent units, but again, thank you all so very much for watching, and enjoy life.